Here's another short video just to kind of set up the where we're going with the infinite series. I just want to make this abundantly clear that there's several different notations that are new to you, so you want to make sure you understand all of them. So the first thing is the sequence. We've talked about that quite a bit now. You should know what a sequence is. We usually represent it with an A sub n. But it could be a B sub n or C sub n or D sub n, but the main thing is there's no sigma notation in front of it, right? So a sequence is just an ordered pair of, or ordered list of numbers that have some kind of a pattern to them. And we can express them with an explicit formula or a recursive formula. And this is showing you an example of this a sub 1, a sub 2, comma, a sub 3. So again, it's emphasizing these are just a list. They're not added, they're just a list. Okay, so then the second thing is that you need to understand is the series. A series is the terms of a sequence added up. Now we can add all of the terms of the sequence up, and then we call it an infinite series. Or we can just add part of the terms up, and then we call that a partial sum. So here's the notation again. An infinite series is running from n equals 1 to infinity, which means we just keep plugging numbers in. The numbers that I'm plugging in get bigger and bigger without bound, which essentially means we never stop adding. We're going to be adding for the rest of our lives. And notice there's a dot, dot, dot here with nothing on the other side. The partial sum, on the other hand, starts at n equals 1 and goes to some, well, actually it doesn't have to start at 1, it could start anywhere, but in this case starts at 1 and goes to some finite number. K would be a number in an integer, because the indices of a sigma notation are always integers. But but notice on this one that you go a sub 1 plus a sub 2 plus etc., 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 to the one right before the last one, and then the last term. And the last term is the term that we plug that we get when we plug in k into the explicit formula. So we got sequence, we got a series that can be expressed as an infinite series or a partial sum. Those are three different things. And then there's one more thing, and this is the one that really adds confusion to this, is there's a sequence of partial sums. So notice it says sequence. So it is a sequence, but it's different than this sequence. This sequence is just made up of the terms. This sequence is made up of a bunch of partial sums. That's why it's called the sequence of partial sums. So the first term of this sequence would be a sub 1. The second term of the sequence would be a sub 1 plus a sub 2. The third term of the sequence would be a sub 1 plus a sub 2 plus a sub 3, etc. Now I'm going to point out a mistake I made in the first video. I think I used this notation to represent a partial sum, and I was incorrect. This notation usually refers to the sequence of partial sums. So just wanted to make sure, or just point that out, that from now on I'll be using it this way. So again, this sequence could go on forever also, just like the first sequence, but it is made up of a bunch of little partial sums. Okay? And this one here is really important for what we're going to say next, because, of course, the real question is, what does it mean when we say an infinite series converges? Because, again, if you're adding up an infinite number of things, then how could it converge to anything? Because you're just going to keep adding and adding and adding, right? So what it means when we say an infinite series converges is we're saying that an infinite series, that's this notation, right, converges, and that's not, it's not that I don't know how to spell if. This is a notation that means if and only if. So it means this is true if that's true, and vice versa. So the infinite series converges if and only if the limit of the sequence of partial sums as n approaches infinity approaches a finite number. So you remember how limits work. We can take a limit without ever. We can look at what's happening as something approaches something, and we don't have to actually get there, which is the case with when we're adding up infinite series. We never get anywhere because we just keep going, because we keep adding an infinite number of terms. So the way we deal with this is we look at this and say, we look at the limit of the sequence of partial sums. So you can see as we go out this sequence, we are getting closer and closer to the sum of the infinite series. The more terms each term we go further, the closer we get to the actual sum. So at this point, if this limit is approaching a finite number, then that means we would say that the infinite series converges. If this limit is just getting bigger and bigger without bound, then we would say the series diverges. Or even if it's bouncing all over the place, which is a possibility, then we would also say that it diverges. Okay. So if the limit exists and it's a finite number, then the infinite series converges. If the limit does not exist, or is equal to infinity or negative infinity, then we would say that it diverges. Okay, but again, know what this sequence is. This is a sequence of partial sums, not the original sequence. So just a real quick example. Let's say the sequence is 2n plus 4. So a sub 1. So if we just list the terms of the sequence, a sub n is, the first term would be 6. The second term would be 8. No, it wouldn't. Yeah, it would. 8. The next term would be 10. Next term would be 12. The next term would be 14. And we can just keep producing these all day long, right? So then the infinite series that goes with this, so we'd go let a sub, or we would let n equal 1 to infinity. So of a sub n, that would be 6 plus 8 plus 10 plus 12 plus 14 plus dot 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 on forever. An example of a partial sum would be n equals 1 to 4, let's say, of a sub n. That would be 6 plus 8 plus 10 plus 12, which equals 36. Okay? And then finally, the sequence of partial sums would look like this. It would be 6, comma, 14, comma, because that's 6 plus 8. 24, comma, 36, comma, so there's that fourth partial sum. Notice it's the fourth term in the sequence. And then we'd add 14 to that, so that'd be 40, 50, etc. And we could keep producing these all day long. So here's the sequence. There's the infinite series associated with that sequence. Here's an example of a partial sum associated with that sequence. And here is the sequence of partial sums that also goes with those sequences. So now, the question of whether does this infinite series converge or diverge? Well, we can look at this right now and tell that it is just going to get bigger and bigger without bound, right? Because each turn of the sequence is getting larger. It's jumping up by more each time, actually. Notice from here to there it's 8. From there to there it's 10. From there to there it's 12, right? So this thing is just going to get bigger and bigger without bound. So we know that this thing diverges just by looking at it. And if you think for a moment, you'll recognize that this original sequence is a arithmetic sequence. And it totally makes sense that that thing would diverge because you're adding a arithmetic sequence that's growing like this. Is every term that you add is bigger than the last term. So we can make a general rule that a sequence, an arithmetic series, so that means you're adding up the terms of arithmetic sequence, will always diverge. Okay? Series diverge. all of them. Let's look at another example. A sub n is equal to, say, 2 times 3 to the n. So that means that my first term is going to be 6. My next term is going to be 18. My next term is going to be 54. My next term is going to be, 150, 1262, etc. And if we do the infinite series, that's going to be 6 plus 18 plus 54 plus 162 plus ... If we do a sequence, or if we do a partial sum, for the 3 this time, that would be 6 plus 18 plus 54, which would be, 60, 78. If we do the sequence of partial sums, that would be 6, 24, 78, there's that third partial sum. And we can keep going. Let's see, that'd be 230, 240, etc. And again, we notice that this thing is just getting bigger and bigger without bound. Notice each term of the sequence is bigger than the last, obviously. So if we asked about this, whether it diverges or converges, we would say the infinite series then diverges. Okay? So does every one of them diverge? Well, let's look at one more. A sub n equals, let's say, 64 times 1/2 to the n. So my a sub n would be 32, 16, 8, 4, 2, 1, 1/2, etc. The infinite series would be 32 plus 16 plus 8 plus 4 plus ... We'll skip the partial sum this time and go right to the sequence of partial sums, and that's going to be 32, 48, 48 plus 8 would be 56, 60, 62, 63, 63.5, ... So now we want to take the limit of this thing as n approaches infinity. So it seems like we have some hope here, because definitely the terms that are being added are getting smaller and smaller and smaller. So both the previous two examples, the next term in the sequence was always bigger than the term before it. In this case, the sequence is getting smaller. So that gives us some hope. And we'll talk about how to determine this later, but I'm just going to jump to the point that this sequence, or this infinite series, actually converges. Because if you take the limit of this sequence, these terms are getting closer and closer to a number. You can see that it started out, they were not anywhere close to 63, but it quickly got close to 63, and now it's just, if we keep going, you can see a couple more here. Like if the next one is going to be 1/4, right? So that'd be 63.75. So you can see its growth rate is really slowing down. So this is going to converge to a finite number. In other words, there'll be a ceiling that this sequence will never go over. So in that case, we would say this infinite series converges. And again, we'll get into details of how we know that later, and actually what we're going to do eventually is we're going to have to show that. We're going to have to prove that that's true. Okay, so there's but the key, the real key to this video is really distinguishing the difference between the sequence, the infinite series, the partial sum, and the sequence of partial sums.